Okay, so welcome to another session on maths for data sciences. So till now we have been looking at how to compute the expected value and the variance of some of the discrete distributions. So we looked at uniform distribution, then we looked at binomial distribution, then we looked at Bernoulli distribution, which is a general like for n equal to 1, if we put binomial n equal to 1, it becomes a Bernoulli distribution. And then we looked at geometric distribution. So for binomial distribution, we looked at the mean value computed as NP, where n is the number of trials and p is the probability of success in each of those n trials. And the variance was computed as n multiplied by p into 1 minus p. For Bernoulli distribution, where the parameter is theta, we looked at mu as theta itself, while the variance calculated as theta into 1 minus theta. For geometric distribution, where the parameter is p, the mean was computed as 1 upon p, while the variance was computed as 1 minus p upon p square. So these were the various ways, various distributions for which we looked at the expected value and variance computation from very basics using their probability mass function and using the generic definition of expected value calculation, which was summation of x time multiplied by px, which means we multiply each value of x for that distribution with their corresponding probabilities and we add all those values. Similarly, the variance was computed as expected value of x square minus the square of the mean computed. So using these two very basic computations, we were able to get the expected value and variance of these four discrete distributions. Now going forward, we are still left with one of the distribution, which was Poisson distribution. Now to derive the mean and variance for Poisson distribution, what we'll be looking at, Taylor series first, because this is a concept which would be used to get to the derivation of Poisson distribution expected value and variance later on. Now a Taylor series is nothing but it is like a function of an infinite sum of terms that are expressed in terms of the function's derivative at a single point. Now let us say we have a function. Now this could be any function. So let us say we have a function, this kind of a function, and we call this fx. Now let us say we have to compute the Taylor series at a particular point. So let us say we are computing it at x equal to a, and we need to find the expansion at this particular point for this particular function. So what we do is at this particular point we already know the function, so we can easily compute the function value at a. We also can calculate the first derivative of the function and then put the value a, and similarly we can calculate the second derivative and put the value a, and so on. Once we have done this, we put these values in Taylor expansion to get the required function value of x minus a. So this is how we get the Taylor series for any function at a particular point. Now another generic definition of a Taylor series could be something called a Maclurian series. So we call it. What this does is it gives you the generic definition of the function itself in terms of infinite terms. So what we do here, we simply put a equal to 0. So if we put a equal to 0 in Taylor series, it becomes a Maclurian series. So if we do that, we get fx equal to f of 0 plus the derivative of function at 0 into x, because x minus a becomes x minus 0, which is x, plus f second derivative value 0 upon 2 factorial into x square plus third derivative at 0 into x cube upon 3 factorial, and similarly this is an infinite sum of these kind of terms. Now let us say we already know, so let us say we take a particular function let's say we take 1 upon 1 minus x. Now the first derivative of this function can be calculated as minus 1 upon 1 minus x whole square, and then there will be a minus 1 because we'll have to do the chain rule. First we find the derivative of 1 upon t, where t is 1 minus x, and after that we multiply it by, so we basically are doing d of 1 by t and d of t to get to the whole derivative, and derivative of 1 minus x is minus 1, therefore we are multiplying it by minus 1 again. So we get 1 upon 1 minus x whole square. Similarly, for second derivative, we do minus 2 upon 1 minus x whole cube, and once again derivative of 1 minus x is minus 1, and therefore we get 2 upon 1 minus x whole cube. Similarly, the third derivative now, it can be calculated as 2 into 3 upon 1 minus x raised to power 4, which is 3 factorial raised to power upon 1 minus x raised to power 4. So this is how we can get each of the derivatives here. Now let us say we want to calculate the Maclurian series for this particular function. So what we do, we put, so we know f of 0 is nothing but is 1. F derivative, first derivative of f at x equal to 0 would be 1, because 1 upon 1 minus x whole square is 1. Similarly, the second derivative and value at x equal to 0 would be 2. The third derivative, value at x equal to 0 would be 3 factorial, and so on. So once we have done that, we put these values in our Maclurian series, this particular series which we got here, to get the required result now. So let us say we have fx equal to f of 0 is 1 plus f derivative x at 0 is 1 into x, so we are left with x, plus double derivative of f at 0 was 2, so we have 2 factorial x square plus 3 factorial upon 3 factorial x cube, and so on. So if you look at it, this becomes a generic series 1 plus x square plus x cube till infinity. Now we know that this particular series is nothing but if we use sum of an infinite geometric progression with the first term as 1 and common ratio as x. Since we are multiplying each consecutive term by x, we get the sum here as a upon 1 minus r, which is 1 upon 1 minus x, which was our original function, and therefore we have been able to validate the Taylor expansion or Maclurian expansion using this particular function 1 upon 1 minus x here. So now this proves that a Maclurian series is able to give a value of this function in a sum of an infinite terms, where each term is either a function value or some derivative of that function multiplied by x raised to power n upon some factorial. So basically we have to just remember that this particular Maclurian series could be used to get the expansion for any function in general. Now for Poisson distribution specifically, we would be looking at another expansion, and the function in this case would be e to the power x. Now the first derivative of e to the power x is the same as e to the power x, and therefore we have e to the power x here, and similarly the second derivative is also the same. So since we have all the derivatives as same, the value of each derivative at x equal to 0, for which we use for Maclurian series, would also be same and equal to 1. So once we have done that, we simply put these values in our Maclurian series, this particular series, and f of 0, which is 1, then we have x, then we have x square upon 2 factorial plus x cube upon 3 factorial plus x4 upon 4 factorial, and so on till infinity. So now one has to just remember this, because this we would be using in the derivation of the expected value for Poisson distribution as well as variance for Poisson distribution. Now once we have done that, we'll go towards the Poisson distribution and we'll see how we can get to the expected value. Now for any distribution, we earlier saw the mean or expected value is calculated as the sum product of the value of that variable multiplied by the corresponding probability of that value to occur for that particular distribution. Now for Poisson distribution, we saw the probability mass function is defined as lambda raised to power x e to the power minus lambda upon x factorial. So again, this whole term is in summation right now, and we know that this summation goes from x equal to 0 to infinity. If you remember, Poisson distribution can take 0 as well. Now once we have done that, we just cancel this x with this x factorial, so we'll be left with x minus 1 factorial, and we have lambda raised to power x e to the power minus lambda upon x minus 1 factorial. Now if we bring out e to the power minus lambda out of summation, because we can bring it out because this is not a function of x and therefore there is no variable here, and we have summation of lambda raised to power x upon x minus 1 whole factorial. Now if we start putting values here for x from 0 to infinity, we'll have 1 upon, so 0 minus 1 factorial is not defined, so this will only start from x equal to 1, and therefore the first term would be lambda, and 1 minus 1 factorial, 0 factorial is always 1. So for x equal to 2, we'll have lambda square upon 2 minus 1 factorial is 1 factorial plus lambda cube upon 2 factorial plus lambda 4 upon 3 factorial and so on till infinity. If we bring lambda out, we are left with 1 plus lambda square upon 2 factorial plus lambda cube upon 3 factorial and so on. Now here comes the interesting part where we'll be looking at this particular term. If you remember from Taylor series, which we saw just now, the expansion for e to the power x was given as 1 plus x square upon 2 factorial plus x square upon 3 factorial plus x4 upon 4 factorial and so on. So if we put x equal to lambda, we'll have e to the power lambda as 1 plus lambda square upon 2 factorial plus lambda cube upon 3 factorial and so on till infinity. Now this is the same term which is there in this particular bracket, and therefore we can write this as e to the power minus lambda and e to the power lambda. Now this and this cancels out and we are left with lambda, which is the required expected value for a Poisson distribution. So for a Poisson distribution, the mean or expected value is given as lambda. So this is how we get to the expected value or mean of a Poisson distribution. Now that we have looked at the mean, we will be moving on to the variance of the Poisson distribution. Now for variance, we need to calculate the second movement of x and then subtract the square of the mean which we just calculated from the second movement of x. To calculate the second movement, we need to calculate the summation of x square and probability of x taking the value of x, which is summation of x square lambda raised to power x e to the power minus lambda upon x factorial. Now this becomes a little tricky here. So what we do is we write x square as x into x minus 1 plus x, because minus x from this first term plus x cancels out and we are left with x square, which is the value we are putting here, and then rest of the terms remains same here. Now what we do is we divide this into two terms, the first one being summation of x into x minus 1 upon x factorial lambda x e to the power minus lambda, and the second one being summation of x upon x factorial lambda x e to the power minus lambda. Now here in the first term, x into x minus 1 gets cancelled, so we are left with 1 upon x minus 2 factorial lambda x e to the power minus lambda, and in the second we just cancel x, and therefore we are left with 1 upon x minus 1 factorial lambda x e to the power minus lambda. Now if you look at it carefully, if we expand this particular term, we would be left with lambda x e to the power minus lambda upon, so we cannot have x equal to 0 or x equal to 1 because then this factorial will not be defined. So we start from x equal to 2 till infinity, and we have, so for x equal to 2 we can write this as lambda square e to the power minus lambda divided by 0 factorial plus lambda cube e to the power minus lambda upon 1 factorial plus lambda 4 e to the power minus lambda upon 2 factorial, and so on till infinity. Now if we bring out lambda square here, we are left with e to the power minus lambda plus lambda e to the power minus lambda upon 1 factorial plus lambda square e to the power minus lambda upon 2 factorial, and so on till infinity. Now the interesting thing here is this particular function inside the bracket, this is nothing but sum of all probabilities for Poisson distribution with parameter lambda. Because if you remember, the probability mass function for a Poisson distribution is given as lambda raised to power x e to the power minus lambda upon x factorial. Therefore, if you look at P0, it is lambda raised to power 0, which is 1. So it is e to the power minus lambda. Then P1 is nothing but lambda e to the power minus lambda. P2 is lambda e to the power minus lambda. So it's lambda square actually divided by 2. Now all these terms are nothing but the ones which we are looking at the bracket inside the bracket here, and therefore we can actually write this as lambda square summation of px equal to x. So we are just summing up all the probabilities here, and we already know sum of all probabilities is always 1. Therefore this particular term comes out to be lambda square. Now once we have done that, we will also try to look at this second part here. Now one can imagine this is very similar analysis what we did for the first part. This will again start from x equal to 1 to infinity, and we'll have lambda e to the power minus lambda plus lambda square e to the power minus lambda upon 1 factorial plus so on. This again we take out lambda and we'll be left with minus lambda plus e to the minus lambda upon 1 plus lambda square e to the minus lambda upon 2 factorial, and so on. Now this is summation of again px, which means we are again, the bracket contains the sum of all the probabilities for the Poisson distribution with parameter lambda, and this has to be 1, and therefore we are left with just lambda here. Now that we already know the second moment of x square is lambda square plus lambda, we can calculate the variance as second moment of x minus mu square, which is lambda square plus lambda minus lambda square, because mean of the Poisson distribution we earlier computed was lambda, and therefore we are again using it as lambda square here, and we are left with lambda itself. So for the Poisson distribution, the mean and variance for a Poisson distribution are both actually equal to lambda, and one has to remember that we use a Taylor expansion to get to these expected value and variance of a Poisson distribution. So this is it from this particular session. I know there was a little more maths involved. Now that we have reached end of this session, I promise we'll have something of maybe less maths in the next one.